n convolved with h of n. Very important. It is a convolution of the input signal with the impulse response of the system. So this can be mathematically calculated as a sigma j is equal to minus infinity to plus infinity x of j delta of n minus j. If you want to find the impulse response as, you know, the convolution of the input sequence with the impulse response. So you could also represent it as not delta, but you could say it as h of n minus j. This can also be represented as h of n convolved with x of n. There is no harm in it because it satisfies the commutative property. Okay, so it could also be represented as sigma j is equal to minus infinity to plus infinity h of j to x of n minus j. N minus j. Okay, right. The next topic is phase and group delay. Phase delay and group delay. Whenever a signal is transmitted through a dispersive system, okay, like a general analog or digital communication system, let's say a communication system where you have the input signal, the channel, and the output signal. So when a signal is transmitted through this kind of dispersive communication system, some delay is introduced. That means the output is obtained after some delay time with respect to the input signal. So you can't expect the output to reach exactly the same time when the input started. So it takes some time for the input to reach the output stage. So that is called the delay. So this delay is determined, usually this delay is determined by the phase response of the system. Okay. Suppose phi of omega denotes the phase response of the channel. Suppose phi of omega denotes the phase response of the channel. And if there is a sinusoidal signal which is transmitted at a frequency omega c, in communication theory we refer to as a carrier signal of frequency fc. So the received signal, okay, so this signal is transmitted. So when it is received by the receiver, the received signal of course should have the same frequency, but this signal will lag the transmitted signal. The received signal will lag the transmitted signal by phi of omega c. Okay, so the phase of the received signal will not be the same as the transmitted signal. That is, the phase response, the phi of omega is what we said, the phase response, right? So phi of omega c will be the phase of the transmitted signal. So the received signal will lag by phi of omega c. So the phase response of the received signal will be, you can say, delayed, or it will lag by the transmitted signal phase response by an amount equal to phi of omega c. With respect to time, because delay is usually measured in terms of time, right? So say 1 millisecond or 2 millisecond as an example. So the time delay, the time corresponding to this delay can be calculated as minus phi of omega c by omega c. Minus phi of omega c by omega c. What does this minus indicate? There is no uh, big reason why we put a minus. The negative sign indicates phase lag. It indicates phase lag, and this time delay is also referred to as phase delay. Also referred to as phase delay, and is denoted by tau p. Tau p, which is equal to minus phi of omega c by omega c. Also do understand that phase delay is not actually the true signal delay. Okay. This signal does not convey any information, because as you know, in communication theory we refer to as carrier signal, right? Carrier signal does not convey the actual information. So it does not convey any useful information. It is only used as a carrier to carry the message signal, and the message signal is the one which carries the original information. So this delay, which we said phase delay, is actually referred to the delay of the carrier signal, and it's not of much importance to us, because this is not the actual signal that is supposed to be transmitted. So this delay is also referred to as carrier delay. The delay of the carrier is phase delay or carrier delay. Now using this carrier we modulate the signal, and the modulated signal is transmitted. So the time delay is also encountered in this modulated signal. So what is important to us is modulated signal, because our message signal is present in this modulated signal. So we are interested in the time delay of this modulated signal, and of course there is a delay for this carrier signal which we can't neglect, but still it's not the actual delay which we are interested in. So the time delay incurred by the message signal in this modulated signal. And where is this message signal? For example, if you take amplitude modulation, so the envelope of the modulated signal is nothing but the message signal. So the time delay incurred by the message signal, that is the envelope of the modulated signal, is given by a delay called group delay. Group delay denoted by tau g, and tau g is equal to, can be calculated as minus d of phi of omega by d omega at omega is equal to omega c. Omega equal to omega c. So minus d by d omega of phi of omega will give you the group delay, and group delay is called as the envelope delay. Group delay is called envelope delay. This is the actual delay. This delay refers to the delay of the envelope of the modulated signal, which is actually a message signal for the case of an amplitude modulation. So group delay is a real delay. Group delay is the real delay. Like, you know, group velocity is the actual velocity of the transmission of a signal. Group delay is the actual delay, while phase delay is not the real delay. Of course it is a delay, you can't ignore that, but it is not the real delay. So delays in general can be classified as a carrier delay or phase delay. The second delay is the group delay or the enveloped delay. So the group delay is actually the true signal delay. So normally the group delay is considered for narrowband signals. But when there is a wideband modulated signal that is transmitted through a communication channel, so each frequency component of this wideband signal will be delayed by a different amount. So every frequency will be delayed by certain amount. So in that case, when such kind of signal, when such kind of wideband signal is reconstructed at the receiver end, so care should be taken that the overall group delay is taken into consideration. Okay, because every frequency has a tendency to get delayed in its own way, which is not controllable. So this group delay needs to be considered, and proper reconstruction should happen at the receiving end. So the important points to be understood in this topic is how to calculate phase and group delays, tau p and tau g's. Tau p is a phase delay, that is minus phi of omega c by omega c. Tau g is minus d by d omega of phi of omega, at omega equal to omega c. The phase delay is also referred to as a carrier delay, and group delay is referred to as the envelope delay. And do remember, important one more question, group delay is the actual delay. Phase delay is not the real delay. Like group velocity is the actual velocity and phase velocity is not the actual velocity. And group delay needs to be considered, of course, for both narrowband and wideband signals, but normally this group delay is considered for narrowband signals. But if it is a wideband signal, then when you're reconstructing the signal, you need to consider the overall group delay and reconstruct the frequency components, because each frequency component can be delayed by a different amount.